Okay, can you see this web work problem and me writing on the screen?
Yep.
Yeah.
Okay, and I am recording. So we found out that the equation of a sphere last time was this. So this is what x, y, z is all points on the sphere. And by the sphere, we mean just like if you think about a balloon, it's just like the material, the rubber of a balloon. Okay, that's the points on the sphere. And those are every point x, y, z. The center is not a point on the sphere. It's the geometric center of all those points, but it's not a point on the sphere. That's ABC. And then the r is the radius, the distance from that center point to every point on the sphere. That's the radius. R is the radius. And we did this by making a vector and finding the magnitude of that vector, right? The magnitude of the vector was the radius, was the square root of the sum of the squares of the components of that vector from the center to any point on the sphere. So this came right from the magnitude of a vector. And that built the equation of a sphere for us. Okay, so if you had all point, if you made this like greater than, then you would be taking all points that are further away than the radius of that sphere. So it would be like every point outside of the sphere if you did greater than. And then if it was less than, it'd be like every point that's a distance less than the radius. So that would be all the points inside the sphere.
Would it be less than or equal to, or greater than or equal to, or just greater than? Or?
Well, it depends. Those both have valid meanings. So less than would be everything inside the sphere. Less than or equal to would be inside the sphere and the shell of the sphere itself. So that those both have, you know, all of these have valid meanings for some set of points, right? So this includes, these would all include the sphere itself. These would not include the sphere. It'd be everything up to the sphere, but not including it. Okay, so then this is not in standard form. So you have to do what's called completing the square to get these perfect squares to get the standard form of the sphere. So the rule for completing the square is you look at the coefficient, the linear coefficient, and you take half of it and you square it. So half of -12 is -6, squared is 36. So that just completed the square for x. And then similarly for y, half of 4 is 2, squared is 4. Half of 6 squared is 9, right? Half of 6 is 3, squared is 9. But if I add all those numbers to the left side, I have to add all those numbers to the right side. Does that make sense so far? Perfect. Now I've got perfect squares because I took half of the linear coefficient and squared it. I've got perfect square trinomials. For instance, this is x minus 6 squared. And this is y plus 2 squared. And this is z plus 3 squared. And so you see now it looks like our equation of our sphere here. What is this? 12, 60, this is 25. And you can take it from there. So you need to complete the square on any terms that you need to get this form of our sphere. Any questions on that? Okay, let's look at the last problem, number 11. That seemed to have caused a little more difficulty. So here you have these sphere, and that one of the diameters has endpoints. So let's make a picture. And so 1, -8, 7, which octant is that in? 1, -8, 7. 1, -8, 7. What octant is that?
Is that the third one?
The third?
Fourth.
Octants are right in front here. This is 1, 2, 3 is back there. That would be octant 4, right? X is positive, Y is negative, would be the fourth quadrant, also fourth octant because Z is positive. And then 4, negative 2 is also. So those are both in the, and I did not draw these accurately, but I'm just kind of doing it. So we have this diameter for a sphere in the fourth octant. So what do we need to write the equation of the sphere? We need the center and the radius. So how do we get the center if that's a diameter? Well, the center is exactly what halfway between those 2 points. So each of the coordinates is going to be halfway between each of the 3 coordinates. So that's a hint for that one. So you want halfway in X, halfway between these 2 values in Y, and halfway in Z to get the center. And then once you have that point, you have the center point and a point on the sphere, you can find that radius using vectors. You can make a vector and find that radius. In terms of what they want here, so they're moving that r squared, they're subtracting it from both sides. So what you're going to put in that box is going to be x minus a squared, y minus b squared, c minus z squared, and then you're going to put minus r squared would equal 0. So by doing the equals 0, they're saying subtract the r squared and move it over to the left-hand side. So maybe that was part of the difficulty getting this one right also. Okay, questions on this one? Okay, let's jump into that dot product that you're working on, this dot product, and I told you how to find it. You just multiply the like components and then add those all up and you get a number, right? So a dot product is multiplying 2 vectors together and you get a scalar. That should have been one thing that you discovered doing that. So let's go back here. Can you see the worksheet?
Yep.
Yes.
All right, and so you drew the original 2 vectors for all these, and then you found the dot product. So those are both 5, 0 and 25, then 5, 0 and 4, 3, and you got 20, and then 5, 0 and 3, 4, and you got 15, 5, 0, 0, 5, you got 0. Are these familiar?
Yeah.
Negative 15, negative 20, and negative 25. And then you got, so when you work the ones below, you got these same values. You got these same values, and the idea was to try to make some observations, some generalizations about what this number means relative to your original 2 vectors that you're taking the dot product of. And so one generalization you might have came up with was when the vectors are at a right angle, and for vectors we call that perpendicular, of course, but orthogonal. Orthogonal means at a right angle, but it just also applies to higher dimensions when you can't really conceive it as being a right angle in 4, 5, 6 dimensions, but you still have this principle of orthogonality, right? So orthogonal, the dot product was 0. When it was the same vector, you get the same vector, you get 25. And what does 25 have to do with these 2 vectors? Where does that number come from?
AX times BX.
Okay, but yeah, so that's the formula for it. But what's another way to
also a
think of
squared.
25 relative to these 2 vectors?
A squared.
What's the magnitude of this first vector?
5.
5. What's the magnitude of this vector?
5.
5. So this is the product of the magnitudes. This is the product of the magnitudes. But you only get that exactly when they're the same vector. And what happens here when they're the opposite vectors? You get
get
the
an opposite?
opposite of the product of the magnitudes. So it's still kind of product of the magnitudes, but opposite direction. Or so opposite sign, right? Negative. Okay, so then what about this? How can we see this 20 kind of in the same way as, is it product of the magnitudes? Is 20 the product of the magnitudes of these? So actually, yes and no. So literally no, right? Literally no, because these still both have magnitude 5. But it's kind of still is product of the magnitudes if you think about how the direction is involved, right? So what is it? It's really the product of 5 and 4, which is what? The
projection on the x-axis.
or the what? The x component of this thing, right? Or the component of this that's in the same direction as this. So when you take as much of this vector as is in the direction of this, then it's the product of the magnitude still. Do you see that? It's still as much of this one, 4, as is in the direction of this one, 5. Same thing here. How much of this vector is in the direction of this one? 3, right? Isn't 3 of this vector in the direction of this one? And so then we have 3 times 5. How much of this vector is in the direction of this vector?
0.
None, right? So orthogonal means they have no commonality in direction. They're facing exactly in different directions. There's no part of this that's parallel to this. Therefore, dot product was 0. And then we got to see the same thing when they're apart. So that the amount of this one in the opposite direction is 3. So negative 3 times 5, negative 15. Negative 4 times 5, negative 20. And then we're back to product of the magnitudes again, but in opposite directions. Okay, so let's kind of summarize this. So the meaning, this meaning to the value of the dot product is going to be important as it's applied to lots of different concepts throughout the course. So let's. Can you see my PowerPoint here?
Yeah, I can see it.
Sweet. Okay. So dot product, what does it mean? When the vectors A and B have the same direction, then the dot product is the product of the magnitudes. When the vectors have opposite direction, it's the opposite of the product of the magnitudes. Okay. When they're orthogonal, perpendicular, the dot product is 0. Okay. If the vectors are such that A has a component in the same direction as B, or in other words, there's an acute angle, then it's positive, but less than the product of the magnitudes. And when they're obtuse, so A has a component in the opposite direction of B, it's negative, but less negative than the opposite of the product of the magnitudes. So if we put that all together, there is one particular meaning that brings all of this together, and that the dot product is, it's a type of product of the vector's magnitudes. But there's a caveat, right? There's a condition, but only as much as the vectors are in the same direction. So to the extent that the vectors are in the same direction, it's the product of the vector's magnitudes. So if they're in the same direction, it is the product of the magnitudes. If they're mostly in the same direction, then you're going to get a number almost as much as the product of the magnitudes. In fact, it's going to be the product of one of magnitude times how much of the other one is in that direction. So this is going to be an important concept to keep in mind as we're in applications that use the dot product. Okay, does it make sense? So let's do that. So let's do work. So we haven't done work in this class yet. Did you know that? Get it? It's a joke. All right, so work is defined
good
as the
chuckle.
total amount of force applied over a distance. We can estimate the amount of work to move an object, a scalar quantity, by observing the force applied and the displacement of the object. All right, so we know force is a vector quantity and displacement is a vector quantity. So when you apply a force and it moves an object, those are both vectors. And so then we're going to figure out how much work is done when that force is applied to move that object. So a girl pulls a wagon with a force of 56 newtons at an angle of 39 degrees above horizontal for a distance of 8.1 meters. What's the work applied to the wagon by the girl? So should have written down here first. That's the scalar version of work is that work equals force times distance. So that's if you just like your force and your distance are in the same direction, then vectors aren't needed. It's just the magnitude of the force times the distance that you go gives you the work. But now we know that like force and displacement are vectors, right? So we can have varying directions. So we want to investigate that. So the force that the girl is pulling with is 56 newtons. And then the displacement, she's walking 8.1 meters. So these are the magnitudes of those two vectors, right? So she's pulling kind of up at an angle and she's walking, say, from here to here. And so what's given in the problem is the magnitudes of those vectors. So let's write F and D in component form. So this is a good kind of quiz, a self-check to see if you're keeping up in the course. I want to write F as components. And D as components. All right, so maybe D is a little bit easier to start with. So we need an X and Y component for D. So what's the X component? So if we have our standard frame of reference here, X to the right, Y up, what would be the vector D? What would be the vector D?
Would it be 8.10?
Yeah, exactly. All of the magnitude is in the X direction, so it has the whole component, and there's nothing up and down. So 8.10. Okay, what about F? So now F has components, right? F has a horizontal and a vertical component.
For the X, we could do F times the sine of 39. No, that's for the Y. Right. And then for
Okay,
the
so
X,
what would the X be?
I'm gonna get my calculator.
F times cosine 39. F
Right, so it's going to be that
0.5.
the magnitude of force times the cosine of 39 is going to give us the X component, and then times sine will give us the Y component. So there's
The X
F.
component is 43.5.
Okay. Is that what it is? 40? Okay. Yeah, keep those numbers in case we need them. I'm just gonna write it in exact form for now. Okay, so those are those vectors in component form. And so then we ask what component of the force contributes to the work? The X, the Y, or both? What contributes to the work? Well,
Just the X.
yeah, just the X, because the wagon is only displacing in the X direction. So the amount that she pulls up has no contribution to moving this thing horizontally. Okay, so only the horizontal component is contributing here to the work that she does on the wagon. So to calculate the work done, we can do the scalar, and we can use the scalar version now. We can do 56 cosine 39 degrees times 8.1 meters. So just take the amount of horizontal force times the horizontal distance using our scalar formula, and we get this 352.5 joules. So notice, work was the product of the magnitude of force and the distance, but only as much as they were in the same direction, right? We just took the amount of this 56 in the direction of the displacement. What is that?
The dot product.
Yeah, that's what we said the dot product was, right? So it's like the product of the magnitudes, but only as much as those vectors are in the same direction. So that's what 56 cosine 39 is. It's how much of the force is in the direction of the displacement. All right, so notice what this is. This is the magnitude of the force times the cosine of the angle between the vectors tail to tail times the magnitude of d. So what this is now is this is a new way to calculate the dot product. So you guys were doing it as multiply the x's, multiply the y's, and add, and that's valid. But now we see a variation of how to complete the dot product, which is the product of the magnitudes times the cosine of the angle between them, which is what adjusts for how much of the one is in the direction of the other. That's what cosine theta does. It tells you how much of this is in the direction of the other. So doing it the way you did last night on your worksheet, okay? X's multiplied, Y's multiplied. Same exact thing. You still get, it's still back to 5 cosine 39 times a plus 1 because this is 0. So there's the big takeaway here is, big important, there are two ways to compute the dot product in any given situation. So there's two ways to compute the dot product. They both compute the same value. There's the way you did on the worksheet, multiply the x's, multiply the y's, and add. And then there's this way, the product of the magnitudes times the cosine of the angle between them. That will also get you the same value. And that calculation is kind of more aligned with this meaning that we have, right? Product of the magnitudes, in as much as they're in the same direction. That's what cosine does. Okay, so here's an example. How much work is done to push a box from the point -2, 1, 0? So -2, go back. So x -2, 1. So maybe that's like this point right here. And we're going to push that box from -2, 1, 0 up to this point by applying a force. Look at this box here. We're going to push it up from that starting point by applying a force of 7, -16, 0. Right? So 7 in the x direction, -16, so something like this. But that's parallel to the xy plane. There's no z change in that force, so we're pushing horizontally towards the fourth octant. Okay, so how much work? So we saw that work is so we're going to need to find the angle between the vectors, right? So we're going to need the vector from -2, 1, 0, starting point up to P. That'll be a displacement vector. So what that displacement vector will be, final minus initial. 3 minus -2, 5. -6, -7. 2. So that box, as it slides from this point up to this point, will have this displacement vector applying this force to it. So we're going to have to find this angle between the two vectors. We're going to have to find the magnitudes and find the angle between the two vectors, right? Agree with that? In order to figure this out, we're going to have to find the angle between the two vectors.
Yes.
Okay, hopefully some of you are thinking, no, that would be awful, right? We've got these kind of oblique or slanted vectors in three-dimensional space, and finding the angle between those vectors. So I'll redraw F here. I'll put something like that too. That would be a difficult task. But there's a very easy way to do this problem. And it goes back to, there's two ways to compute the dot product. F dot D computes the work, and there's two ways to compute the dot product. So choose the easier way. Finding the angle is really bad here. Well, in a second, it won't be. That will be easier in a second. But if we're just going straight and we want to find the work, we know the work is F dot D, and there's two ways to calculate it. There's this way, that requires the angle, but then there's also what way?
Doing the dot product.
Well, this is doing the dot product too, but it's like the way you did in the homework, right?
Yeah.
So what's my F? My F is 7, -16, 0, dot. We found the displacement vector, 5, -7, 2. So do it the way you did in the homework, right? So there's two ways to compute the dot product. They're both going to get the same value. So it's going to be 35, 7 times 5, plus, is that 112? Check my math. Plus 0 times 2. So we get 147 Newton meters or joules. Or no, foot-pounds, sorry. So the units of work are distant units times force units. So in English or imperial, force foot-pounds, in metric, Newton meters or joules. So in this case, it's 147 foot-pounds. Okay, so did it make sense why we didn't have to find the angle? So yes, the work is equal to this, which is equal to the dot product, but we can use the easier way to compute the dot product, which is just product of the components, add them up, like you did in the worksheet.
What's the point of having the first equation if the second one's always easier?
It's not always easier. So you could be given you could be given the magnitudes and easily find the angle. So it's in this case, this one's easier. So it depends what you're given in the situation.
So wait, so if they give us the work and the force and distance, we can just divide the force and distance to work and we get the angle?
Okay, good. So that was my next question. Now we have a way of a manageable way of finding the angle measure. And that's by using the two different, you have the two different versions of dot product, they're equal, and that gives us a way to solve for the angle. So let's do that. No, I don't want to do that. Come back. Good. Okay. So the 7 times -16, 0, dot 5, -7, 2. That was equal to 147. But that's also equal to the product of the magnitudes, in as much as they're in the same direction. And so we can find the magnitude of F. What is the magnitude of F? Square root of 49 plus 256. 305.
Yep.
I'll just write it this way. Times the magnitude of D.
Should be 49.
Degrees?
No, the 35.
Oh, thank you. That's 7 squared, right? Yes, thank you. 25 plus 49 plus 4. Good. So now, by having the two different ways of calculating the dot product, you can do it by multiplying components and adding, find the magnitudes, and that leaves cosine theta, so it allows you to solve for theta. So you take the 147 divided by these magnitudes, arc cosine.
Wait, is that 25 plus 49 plus 4?
Yeah, so I'm doing the magnitude of this vector.
Oh, okay, okay.
Magnitude of D. So is the roadmap clear for that? So the dot product then gives us a way to find the angle measure between two vectors tail to tail. Because there's two different ways of calculating the dot product, and we can isolate the cosine theta and then find theta.
How did you get D?
D was the displacement. We started the box here, and the box ends here. So how would you find that displacement vector? It starts here and ends here.
Final minus initial.
Right. Final minus initial, right? So it's going to be, I took these components and subtracted these components, and that's the vector displacement from starting point to ending point. Does it make sense?
Yep.
Okay, so we're just not going to take the time to do that. That's just do the math, right? Solve for theta. But now be careful when you're using this, everything has to be when the vectors are tail to tail, right? This is the angle between the vectors when they're tail to tail. So that if you have vectors that are not tail to tail and you're doing this math, you can make a mistake. So make sure this is when they're tail to tail. So that would be this one here. Okay, let's move on. All right, I gotta see the time here. Nine minutes, perfect. Okay, so let's talk about components. So components, I've got this vector here. It has both positive and y, positive y, x and y components. So there's my x component, my y component, right? And if you add those two components together, you get the vector, right? Vector addition. Apply this vector, and then apply this vector in succession, add them. So tip to tail, you get the resulting vector is that one. And we've done a lot of this, dissecting a vector into its components. But what about if I have a new frame of reference? So I don't want the x, those components were based on the frame of reference of x and y. My horizontal component was my x component, and my vertical component was my y component. But what if I don't care about x and y anymore, and I want components of this vector for this new frame of reference? So there would be like the parallel component to that dotted line, and then a perpendicular component. So these orange vectors are also components of this vector, but for a different frame of reference instead of our standard x and y. So we want to come up with a way to get those.
Wouldn't it be really similar to calculating x and y coordinates as the x and y components?
let's play it out and see if your question gets answered. Okay.
Got it.
So that new frame of reference could be given as like a line, but it could be given as another vector. So given this vector A, that's the one, the light blue vector is like determining this frame of reference. And so we're interested in that vector, which is what, parallel to A, and then this vector, which is orthogonal to A. Okay, so how are we going to do that? So let's start by finding just this magnitude. So just what is this magnitude of that parallel component? What would that be? So how can we get that? Well, if we had this angle, what would that magnitude be? That magnitude, I'll just call it M, or I'll just write mag. All right, so mag equals the magnitude from here to here would be what? It'd be the magnitude of B cosine theta. But that looks a lot similar to what?
Finding the x component we use the x as our frame of reference.
Yep, that's true. But it also looks a lot like this, doesn't it? The dot product of those two vectors would be the product of the magnitudes cosine theta. So look, right here, this part of that is the magnitude of that parallel component. So what's another way we could write that magnitude then is what? A dot B divided by what? Magnitude of A. Right, I just solved for this part of this expression, right? We know that dot product is magnitude of A, magnitude of B cosine theta. The magnitude of this parallel component is just magnitude of B cosine theta, which is the same as A dot B divided by magnitude of A. Oops.
Wait, Professor, I have a question.
Yeah.
What do you mean by parallel? What's parallel to what?
The component of B that's parallel to A. This orange vector, do you see that that's parallel to A, or the frame of reference?
Oh, okay. Yeah. I was just confused about yeah. Okay, I'm good. Thank you.
Yeah, sure. Okay, so I got the magnitude. Now I want this vector. How do I get that vector? So I have a direction and I have its magnitude. Well, this is a problem we've done before. I need a vector in the direction of A that has this magnitude. Remember what I do to do that? So we saw this problem. I want to change vector A into what?
A unit vector.
Unit vector. If I take the vector A and I change it into a unit vector, now I have a unit vector in this direction, and I want to scale its magnitude to be the magnitude I just found, right? So I'm scaling a unit vector in the direction of A. That will give me exactly this orange vector right here. Okay, now I can combine this. I can pull this scalar out and make it squared. So then you get A dot B over magnitude of A squared. That's the scalar times vector A gives that vector right there, that orange vector, which is the parallel component of B parallel to A. This is called the vector projection of B onto A, or the parallel component of B in the direction of A. And it's projection because it's like if you shined a light onto this, the shadow vector of B on the line A would be that vector. So you're projecting B onto A, you get this much. You get a vector that's that long in the direction of A.
Right. So the right side of that that problem, the A vector A over absolute value of A vector, that's the orange vector we're looking for.
This whole thing is the orange vector we're looking for.
Okay, but the on top of that, the right side of it.
This was the unit vector in the direction of A. Remember how to do that? You divide a vector by its magnitude, you get a unit vector in the same direction. And then I scaled that vector up by the magnitude of this that we found first. So by scaling the unit vector to this magnitude, I get the orange vector. Did that answer it?
Yes, thank you.
So would all of this still work if we were looking at the X and Y plane?
Yeah, but you wouldn't need all that. Yeah, it would, but it's the vectors are given in those components to start with. Does that make sense? So these vectors, when we're using these calculations, we're gonna have the X and Y components already. So we're starting with X and Y components. It's like we're doing a transformation of vector B into new components in a new frame of reference. So yeah, it would work, but it would be like total overkill because that we have the X and Y components from the start.
So this equation here solves for the vectors of A and B, or the orange lines. But
just this one.
So what if just that one? Okay.
Just this one. The whole time we've been talking about just the parallel component.
Okay. Okay. Thank you.
Yeah, sure.
So,
Professor,
so
is this like the orthogonal projection, kind of like in linear algebra? Because it looks like the same formula.
Yeah, it's the vector projection of B onto A. And then this is the scalar projection.
Okay.
Scalar projection means just the magnitude only, the magnitude of that vector of B onto A. So let me summarize. I got the formulas here. So you can check this out in the video. We need to. So this is the magnitude of the parallel component vector is called the scalar projection. It's just how much you have. It's how far it is from here to here. That's the scalar projection. And then the vector projection is the parallel component vector. It's actually that vector. We get it from the unit vector of A scaled by the amount of the scalar projection. Gives us the vector projection. Okay, I'm